All right, howdy there, and welcome to the beginning of Unit 2. Now, before we get too deep into college algebra, I do have to bring up story problems. I know that some of you have been dreading this moment, but I promise I'll try not to make it too bad. The reason we study these is that it's very rare outside of a math class to have a math problem transmitted to you already written in the language of algebra. So it's very rare to see anywhere outside of a math class a problem like 3x plus 10 equals 12, solve for x. We can all do that. It's much more common to see something like, if I had 3 times as many nails in this box as I do now, and then 10 more as well, I would have 12 nails. That's the same equation, but it's in the language of English. Now, problems outside of this class are going to be transmitted to you either in English or through direct experiences, and you observe the circumstances and you decide for yourself what the problem is and how you're best going to solve it. It's really a creative exercise, but it's also an exercise of translation. So the idea is that to tackle story problems, we have to think of translating them first into the language of mathematics, solving the algebra problem, and then translating back. Go ahead and take a moment to read this worksheet on the right side of your screen. Please go ahead and pause the video, and in a moment we'll unpause. Okay, so you've read that right screen. That's my overview of modeling. We're going to get deep into what these steps mean with some practice problems. Let's see, write all relationships equations. So I think that as we use these steps, it'll become a lot more clear. Of course, these are guidelines, not hard rules for solving a story problem. This is just some helpful tips to try to streamline the process of translating a story problem to mathematics in your brain. I don't expect or want you to apply each of these steps in order every time you do a story problem. This is just to get you started. I think over time you'll see that it comes naturally. Okay. So I've also got these copied to our whiteboard notes for your reference later. What I want to do, though, is start with a really simple story problem. And I know that you already know how to solve a problem like this, probably. The goal here is not to get the solutions of any particular problem. The goal here is to see how these steps can streamline the solving of a story problem. So let's say that this is our problem. Two numbers have a sum of 40 and a difference of 6. I'll just write the number 6. Two numbers have a sum of 40 and a difference of 6. What are the numbers? Like I said, a relatively simple problem. Let's go through these steps. So modeling is the art of translating a story problem into an algebra problem. We're going to try to take this problem I've given to you in 2 English sentences and turn it into sentences in math, essentially. All right, first understand the problem. Let's to get an idea of what it's asking. Okay, two numbers have a sum of 40 and a difference of 6. What are the numbers? We're going to reread that problem and take notes of all known or unknown quantities. I'll underline those in blue. So I'm asking, what are the numbers? There are 2 numbers. Might as well give them a name right now. We're going to try to assign variable names to those numbers. Maybe we could call them x and y, since there's 2 of them. And I'll underline relationships in green. We're going to note all relationships given. That's anything the problem tells us about what these numbers have to do with each other. We'll make these into equations later. So I know that they add up to 40, and I know that they're different by 6. So I've decided to call my numbers x and y, and it does not matter one bit what letters you choose. You can name your variables whatever you want. Math works exactly the same way regardless. So we just picked x and y because they're familiar to us. Now we're going to use those. Think of those as being like the subjects of the sentences. Those are the nouns in the language of mathematics. And now the sentences are going to be describing these relationships here. Like they have a sum of 40. So how do I write x and y have a sum of 40? Very good. X plus y equals 40 will do it. And when I say they have a difference of 6, I could say x minus y equals 6. Make sense? So x plus y equals 40 and x minus y equals 6. In this case, both of these relationships were explicitly stated in the problem. If there were some relationships that weren't stated in the problem, we would have to include those. Like in a problem about how far did the train travel, I might need that distance equals rate times time. Or if it's a geometry problem, I might build in knowledge like the area of a square is side length squared. Those are the kind of common knowledge things that we might have to put in on our own. The key is you want to have as many relationships written down as you have variables. So since I have 2 variables and 2 relationships, I'm probably golden. This works 95% of the time. If you have 3 variables and 3 relationships, you're probably in great shape. Very rare to see a case where you need more or fewer. It happens, but it's very rare. So that's usually the golden rule, is if you're done writing down your problem and you see you only have 1 relationship, you might need to bring in something like, if there's a formula we've been using all chapter, that formula is probably a really good contender. So the exponential growth formula, when we're in Unit 4, probably a good idea to bring that in anytime you're starting a modeling problem. In this case, though, we were given both relationships. We have 2 relationships and 2 variables, so it's probably good to go on. Next step, now that this problem is translated to the language of mathematics, it's x plus y equals 40, x minus y equals 6, solve for x and y. Now this is a math problem, and it's written in the language of math. It's always been a math problem, but now it's written in the language of math instead of the language of English. So the next thing we want to do, and this is a little tricky, it's hard to solve a system of equations where you have more than 1 variable involved. But it's really easy to solve an equation, and we're going to be practicing in the next bit of this chapter, 2.6 and 2.7, to solve all different kinds of equations with just 1 variable in them. So if I can somehow rewrite these to just have 1 variable in them, I'm going to be in great shape. And here's how I'm going to do that. I'll take this first equation, x plus y equals 40, and solve for one of my variables. I'm going to rewrite that. I'll subtract y from each side and write x equals 40 minus y. So x plus y, you subtract y, and it's just the x on the left. 40, you subtract y, and you get 40 minus y. So these 2 equations mean the same thing because I kept the balance. And now what I'm going to do is say, if this is the value of x, so x is really equal to 40 minus y, then how I can rewrite an equation in terms of just 1 variable is take this other equation and say this x is really 40 minus y. So I'll put that in where the x used to be, and then finish writing the equation, minus y equals 6. So you see, the only thing that's changed is I've replaced this x with a 40 minus y. That's a really useful step. We'll use that a million times this semester. Its name is substitution. I've substituted one thing for another. Since they have the same value, I didn't change the meaning of the equation. But now look at this, 40 minus y equals 6. This is an equation with just 1 variable in it. So that's usually the trick. You usually end up solving one using substitution, then you can solve the other. So now what I can do is simplify this. All right, that means gather like terms, 40 minus 2y equals 6. I'll go ahead and add 2y to each side. This is a little slower than it has to be, but I like it better with positive numbers. And subtract 6 from each side. So 40 minus 6 is 34. That equals 2y. So first I got the term with the y by itself. So 6, 2y, and 40 are each terms, but now this 2y term is by itself, so I can split off the factor of 2 next. First you want to get the term by itself, and then you can worry about multiplication. We'll divide both sides by 2. 34 over 2 is 17, so that's our value of y. One of the numbers is 17. All right, so we rewrote Step 4, we rewrote all unknowns in terms of one variable. So I said x is 40 minus y. So now I have equations for x and y, but put this a different way. If I have x's and y's in each of my equations, it's difficult to solve. But if I can just say x is really just something we did to y, it's a value I can write in terms of y, then now this second equation just has y's in it, and it's easy to solve. So we solve that remaining equation for that one variable. So what I did here was step 5 is now I've got the value of y. Y is 17. One of the numbers is 17. So now we're going to take that. Once you've got one variable solved for, things are easier from there. This was really writing these down, and writing these down was the hardest part. Writing these into the language of mathematics was the hardest part. Solving was a little easier than that, and now that we've got one solution, the rest is about to become very easy. So solve for any remaining unknowns is what we need to do next. I know the value of y, I need the value of x. Well, I know if x minus y is 6 and y is 17, then y is 17, so x minus 17 is 6. That's actually another substitution right there. I replaced the y with the 17. So then I can add 17 to both sides and say x is 23. Of course, you could probably do that without the algebra. You could just say, well, if they add up to 40 and one is 17, other's got to be 20. But now take a look at this. My original problem, and so this is the rest of step 6. Write your solution in English. Here's what I mean. If I come up to you at a riddle party, and yes, they really do exist, and they're as boring as they sound, but if I come up to you at a riddle party and I say, riddle me this. 2 numbers have a sum of 40 and a difference of 6. What are the numbers? You're not going to look at me dead in the eye and say, y equals 17, x equals 23. Like, I didn't say anything about x and y. That wasn't in the prompt. We added those names so we could do math. You know, you want to say something like, the numbers are 17 and 23. You want to answer the question in the same terms it was presented to you. And then this last step, we've solved the problem, but this is something I really like to do to make sure I've got the right ideas, is I like to go back and read the problem one more time, but with my solutions in. So I could say something like, instead of 2 numbers, I say the names of the numbers. 17 and 23 have a sum of 40. Well, yep, they do. And a difference of 6. Yep, that's also true. 17 and 40 have a sum of, or 17 and 23 have a sum of 40 and a difference of 6. So the numbers are 17 and 23. Very good. We've answered the question that the problem actually asked, and we've met every condition in the problem. So that's an indication that we've got the right answer. All right. So that's how these steps go. You don't have to use every step in every problem, and you don't have to do all the steps in order, but generally these are a great way to translate a story problem into terms that make sense. Let's go ahead and just ramp up the difficulty bit by bit so we can see how these work in more complicated problems. Let's say, okay, this is good. Let's say there's a rectangle. We know we have a rectangle, and let's say we know the perimeter is, how about 14? The area is 10. What are the dimensions? So, first off, we need to understand the problem. What is this asking? When I say, what are the dimensions of the rectangle? That's another way of asking, what is the length and what is the width? So those are the unknown quantities. The known quantities are, we know the perimeter is 14 and the area is 10. Let's just go ahead and use L and W for length and width. That's pretty standard. If you prefer length and height or width and height, you can do that. Again, the names do not matter. Next thing we need to do is write all relationships as equations. Now, this problem, we have an unknown length and an unknown width. We have a known perimeter and we have a known area. We know the perimeter is 14 and we know the area is 10. We're looking for two relationships with our unknowns in them. The good news is we can write perimeter and area as length times width. Now this is where, when I say common formulas relating to the subject, this is exactly what I'm talking about. Like for example, we know that the area of a rectangle is length times width. So in this case, I can write 10 equals length times width. Let's see. The other thing we know is the perimeter. Now, perimeter means the length of all the sides, right? So I know these two sides are lengths. Like these two sides are, of course, the same, right? Because it's a rectangle. Opposite sides are always the same length. Otherwise, it wouldn't be a rectangle. So I know that this side is a width. So my perimeter, I can write L plus W plus L plus W, but I think you've seen this with like terms gathered. We could write P equals 2L plus 2W. And we know the perimeter is 14, so I'll write 14 equals 2L plus 2W. And this is really good for us. We have two unknowns. We have two relationships. So that should be enough. Like I said, normally you have the same number of relationships as unknowns. You can go back and try to look for more relationships if that doesn't work, but like I said, 95% of the time that'll be enough. So we wrote all of our relationships as equations. Use your equations to rewrite all your unknowns in terms of one variable. Okay, let's see here. So I'd like to know what is L in terms of W or what is W in terms of L. It doesn't matter which one I pick. So I have four choices. I could solve this equation for W or L. I could solve this equation for W or L. We really just want to do what's easiest. Now, this equation on the right, if I solve that, say, for W, how would I do that? If I want to get W by itself, it's multiplied by L right now. So I need to divide both sides by L. So that would leave me with W equals 10 divided by L, and that has fractions in it. General rule of thumb is if you can avoid expressions with fractions, you're probably doing, it's easier not to. It's easier not to have fractions. If that's the only way through a problem, then of course we'll do it, but usually there's something more elegant. So let's take a look at this equation. Okay. Looking at this, I could definitely get one of these by itself without fractions. In fact, we've got a greatest common factor here. I can divide both sides by 2 right away. That's not normally how I'd start, but I can say 7 equals L plus W, and that's just a little bit nicer to work with. And now if I want L by itself, all I have to do is subtract W from each side. So I could say the length of the rectangle is 7 minus the width of the rectangle. Now I did switch the sides of the equations there because I'm used to the solution being on the left, but see, I subtract W, so 7 minus W equals L, and then I just switcherooed those. L is 7 minus W. So now I've got the length written in terms of the width. So it's like there's only one unknown now because the length depends on the width. So if I can solve for the width, I know everything. 10 is equal to the length times the width. I'm going to use substitution here. 10 is equal to the length times the width. So 10 is equal to, and I'll put an expression for the length here, times the width. So this is going to be the length, but I'm going to write 7 minus the width because I know that's equal to length, and it's in terms of W. So now this is one equation with one variable, W. I should be able to solve this for W, and then we'll have our dimensions. So, might as well simplify each side, right? 10 is already simplified, but I can distribute this W. 7 times W minus W times W. Shortcut, right? W squared. Now, we haven't talked a ton about this kind of equation yet, but I do believe we saw it in Unit 1. This is a quadratic equation. In Unit 1, we talked about factoring these. We have not talked about solving them yet. So You'll learn how to solve these soon. For now, I'll go ahead and do it. Take this as a sneak preview of section 2.5. I know that I can factor the equation, and that gets me factors, and that's very handy. I don't remember, did I talk about why it's so good to have those factors, about the zero product property? If I can rewrite a quadratic equation, if I can write ax squared plus bx plus c equals 0, if I can just write that as like x plus p times x plus q equals 0. Now look, I have two different numbers whose product is 0. What do you know? If I say a times b equals 0, like 10 and 12 don't work. -3 and -8 don't work. Things like that. If I say a times b is 0, the only way to get a product of 0 is if one of the, what are they called? One of the factors is 0. Right. So if this is just a number, this is a number written as a sum of a variable plus a parameter. But if this number is 0, then we'll have a product of 0. Well, if this number is 0, we'll have a product of 0. But if neither of these numbers is 0, then this can't be true. So now I know x plus p equals 0 or x plus q equals 0. And I can subtract p or q from each side. So x equals -p or x equals -q. So that's why we were learning factoring, it's one small step from factoring to knowing where a quadratic equation is equal to 0. But notice, this only works because we've got a 0 over here on the right. It doesn't work if there's something else on the right? So the first thing I'm going to do is I'm going to rewrite this equation so that one of the sides is 0. Let's go ahead and make it the right side. So I can add w squared to each side. And I can subtract 7w from each side. Whoops, not equals. Plus 10 equals 0. And now if I can factor this thing, we've got it. So this is, see if you can do it on your own, pause and unpause. W minus 2 times W minus 5 is equal to 0. So interesting. We have two solutions, either the width equals 2 or the width equals 5. Do you see how that works? By this logic up here, if the width is 2, then this factor is 0. If the width is 5, then 5 minus 5 is 0. And if the width isn't either of these numbers, then there's no way this product can be 0. So we've got our solutions. That's how solving a quadratic works. We were very close already, but we'll cover this again in 2.5, so don't worry if you didn't click right away. We'll do a lot more of these in a couple of lectures from now. So I know my width is 2 or 5, and my length, now that's 7 minus the width. So I've solved, that was part 5, and now we're in step 6. We want to translate our solution back into the language of the problem, which first means I need to know what the length is equal. It's 7 minus the width. So if the width was 2, then the length must be 5, and 7 minus 2. And if the width was 5, then the length must be 2, and 7 minus 5. Write your solution in English. Okay, so here's why we're getting two solutions. Back originally, this problem never said which side of the rectangle was the length and which side was the width. We labeled it that way, and we could have used width and height or length and height. So those didn't matter. If I switched the L and the W, everything would work just the same. That's what's happening in this solution. The rectangle can be 2 wide and 5 long, or it can be 5 wide and 2 long, but those are really just the same rectangle turned on its side. So it's the same rectangle. I can say something like the sides of the rectangle are 2 units and 5 units. I don't know why I wrote U for units. That's weird. No one does that. Don't do that. 2 and 5, or 2 units and 5 units. Never just U. I don't know why I did that. I don't know why I did that. The sides of the rectangle are 2 and 5. We can check. A rectangle with sides of length 2 and 5 has perimeter 14. Okay, 2 plus 5 plus 2 plus 5, that's 14. The area is 10. Okay, 2 times 5, yeah, that's 10. So the dimensions are 2 and 5. Perfect. So the only difference between that and the first problem is we got two solutions, but they were really the same back in the language of the problem. The other thing is we did have to pull in our own knowledge of formulas for area and perimeter. Let's see. Page. Where did I leave my next problem? I haven't looked at these notes in a semester. I just jumped right in with the lecture. Did I lose them? Oh gosh, did I lose them? Oh, here it is. Okay, excellent. Ooh, all right. So that last problem, that was written in the language of English. They both were. This next one, this is going to be kind of written in the language of direct experience. So you're puttering around the house with your significant other, and they say, look, the rain fell off the side of our house last night. See, the rain's coming down, it pours off the side of the house, and when it hits the ground here, and this is terrible, it's digging a hole. And if we let that go unabated, the entire house is going to slide towards that hole. Incidentally, out of the problem for a second, I know this, your professor, Nathan, I know this because the house I'm renting right now does not have gutters. It does have these holes, and the entire house is leaning to the side. It's noticeable. It feels like you're in a fun house. Oh, well, it's cheap. So your significant other says, hey, could you make me a gutter trough? Could you make me a little gutter trough? And you say, sure, what do we make it out of? And they say, well, I've got a piece of sheet metal. I've got a piece of sheet metal, and it's 12 inches wide and 20 inches long. I've seen gutters made of sheet metal. I think this would work. All you really have to do is crimp it here and here and fold it up, and you can have a little sheet metal gutter. And you say, that sounds like a great idea. So we'll just put that where the hole is, and it'll direct the rain kind of away from the house in a way that robs it of most of its velocity as it's coming down, and that should prevent it from digging any further holes and ruining our foundation. Okay. And you say you have rain barrels. How fast is the rain falling? How much does this thing need to hold? And they say, well, as a matter of fact, I know exactly the answer to that question. This thing needs to hold 360 inches cubed of water. That's what we need to hold it in. So that's going to be the volume. When this thing is completely full, it needs to be holding 360 inches cubed of water. Yeah. And you say, okay, we can do that. And then you think, wait a minute, where are we going to make these folds? Okay, so where are we going to make these folds? This is really an algebra problem. So I think we understand what the problem is asking. The question is, where do I fold? Like, look at it this way. If I fold these right next to the edge here, we're just going to have a really wide, skinny trough, and it's going to hold barely any water at all. It's going to be so shallow, it holds almost no water. But if I fold them close to the center, I'm going to have a tall, narrow trough. And once again, there's just not going to be a lot of water in there. We want to get like a happy medium that holds a lot of water. Actually, if you take calculus, you can solve to find out where you should fold to hold the most water. But in this class, what we can do is we can solve to find out where we should get a specific amount of water. No, you know what? Actually, in section, I want to say 5.1, I'll actually teach you how to solve for the maximum of this problem. But generally, to find maxima and minima, you need calculus. There's one exception. Anyway, that's all way too technical. Right now, we just need 360 cubic inches. So we need to find out what kind of quantities are there in this problem. And here I'm going to go out of order a little bit. I'm going to start with a relationship I know I can bring in, because this is a volume, right? So that tells me this is the volume of a rectangle. I know that that's length times width times height. So we've got a length on this end we've got a width right here, and we've got a height right here. I know that relationship, and I can work backwards from there and try to identify what the quantities are in this problem. Well, the length, the width, and the height. Good news is, if you look at this thing unfolded and then folded, let me go ahead and get rid of this extra dotted line here. Look at this unfolded and folded. I know that the length is 20 inches. That's where this edge goes when we fold it up. So I can say we've got our volume is length, width, height. I know that the length is 20 inches. So now I've got two relationships with my four unknowns here. Oh wait, the volume is 360. So it's just the width and the height, and how can I relate those? Well, let's look at how they are folded and unfolded. You see, when they're folded up, if I look at the edge of this trough, when they're folded up and we're looking at the trough edge on, we've got a height, and a width. And those were all coming from this 12-inch side. So we've got a height here, we've got a width here, we've got a height here. So this is, when I talk about math being relevant in your daily life, this is the kind of thing that I use it for all the time. It's like I'm trying to fix something in my house, like the bathtub doesn't drain, and I'm thinking, what kind of geometry problem do I need to solve? So here's a geometry problem from real life that we've got the height plus the width plus the height, and there's our fourth solution. That has to be 12. So now some of these are really boring, but like length is 20, volume is 360. Those are just one thing equals another thing, but they still kind of count as relationships. If we think of these as four unknowns, then I've got four relationships. And the good news is I can immediately start putting these down in terms of fewer variables. I know the length and the volume. I'm going to merge these first three right away. Do a little substitution here. V equals LWH. Well, V is 360. V equals L20 WH. That's a lot better. Now my unknowns are width and height, and I've got two equations in two variables. You see, somehow like the number of unknowns and the number of relationships are somehow conserved. I turned three relationships into one, and at the same time, I went from four unknowns to two. So 4 and 4 is kind of the same situation as 2 and 2, if that makes sense. That's why I say normally it's the same number, because if we can turn that into 1 and 1, now this looks like a pain in the butt to solve. I am going to go one more step and divide both sides by 20. So that means that 18 is width times height. I don't really want to introduce a fraction at this point, so I'll take this other equation, width, oops, almost jumped ahead, plus 2 height equals 12. And I'll go ahead and subtract the 2h. So width equals 12 minus 2h. So I've got the width written in terms of the height. And now I can take that width and substitute it in here. And then I'll have one equation in one variable. So I'm going to say 18 equals. Now, when you substitute something, the entire width, not just one term of it, the entire width is multiplied by the height. So to symbolize that, I need to say this entire thing all grouped together. When you want to say this entire thing all grouped together, parentheses are the grouping symbol. I want you to always think of parentheses as a grouping symbol. That's important enough to write down. Parentheses are how I say, I want this entire expression to all be multiplied by h. So h is multiplied by the whole thing, not just by one part. That's what parentheses do in algebra. That's their main function. So I'll put in this expression. And now this entire thing is going to be multiplied by h. And it looks like we're in pretty much the same situation as the last problem now. We're going to be solving a quadratic in a moment. So I'll write 18 equals, I'll distribute the h now, 12h minus 2h squared. There's a couple of things I can do here. I know that I'm better off if everything's on one side, so I'll add 2h squared. And subtract the 12h. One more thing, I've got a greatest common factor of 2. If I'm trying to factor this down, I'm going to divide both sides by 2. That'll make things a lot easier. Now the leading coefficient is 1, and we can use that sum product method we like. Feel free to pause if you want to guess it yourself. Otherwise, I can go right ahead. Okay. And our factors are h minus 3. Both of them. -3 plus -3 is equal to -6. -3 times -3 makes a positive 9. So one of these factors has to be 0 in order for the product to be 0, right? So if I say h minus 3 equals 0, I can just add 3 to both sides and say h equals 3. So we've got a solution for one of our variables. And now we need to take that and go all the way back and think about what was the original context of the problem. So I'm going to take this diagram here. Actually, let me just both of these. Can I please? Here we go. It's a short tap. So we've just found out that h equals, oh my goodness, nope. No, did not want that. Did not want that. Aha! Here we go. Well, piddle. There we go. Okay. Honestly, I'm much more used to Windows, but this thing's growing on me. Okay. Whoops. That's gone. Okay. Nope. There we go. Okay. So here's what we know. Is now we know the height is 3. And we know h plus width plus h is 10. So this trough right here, this is 3, and this is 3. If the whole thing's 12, then in the middle here has to be 6. So we take our piece of sheet metal, we measure 3 inches in from each side, we fold that upward, and now let's check and make sure that our significant other said that they wanted 360 cubic inches. We know that the length is 20. We know that the height is 3, and we know that the width is 6. So the volume is 3 times 6 times 20, and that is 18 times 20. I like to do 18 times 2 and then multiply by the 10. Just leave the factors of 10 until end. So 18 times 2 is 36, times another 10 is 360. So we have met the specifications of the problem. We have created the correct gutter spout. Incidentally, just because I do know calculus, this is the biggest gutter spout we could possibly make. If we folded these a little bit further in or a little bit further out, the gutter spout would not be as big. So hopefully that illustrates how to solve one of these. Oh yeah, that example is awful. I'm not doing that. Here, let's do one more. If you get it, you can turn off the video at this point. But if you want to see one more, please feel free to join me. I'll do another. I don't know why I act like I'm giving you permission. Of course, you can turn me off at any time you want. I am just a voice coming from your computer. But let's say train A. Yeah, here we go. Here we go, trains. Train A leaves the station going 60 miles per hour. Oh, yeesh. That's not penmanship. I know none of this is penmanship, but that was especially bad. Train B leaves 1 hour later going 65 miles per hour. When will they meet? Step 1, understand the problem. Okay, we've got 2 trains. One left first, the other left an hour later. The one that left an hour later is going faster, so it's going to overtake the first one. But, man, what do we know? We know their speeds. I'm going to use R for rate. Now I run into a little bit of a problem because I've got two different trains. Train A, let's call it rate A, and let's call this one rate B. These are subscripts. I like to use subscripts when I want to use the same letter twice, but I want them to mean different things. So the rate, I could say rate R sub A is how I would pronounce that if I were reading it in math. The speed of train A is how I would say it in English. So the subscripts are like, well, which train is this at the rate of? When will they meet? So we've got some kind of a time going on. We know that this one leaves 1 hour later. That has something to do with time. We're trying to find out what time they'll meet. A lot of moving parts in this problem. Not just because trains have a lot of moving parts. The algebra has a lot of moving parts too. I'm going to work a little out of order again. Like in the last example, I said, well, we know volume is length times width times height, and that kind of informs what variables we need. This time, there are no relationships given in the problem, but the common knowledge relationships that I want to spice things up with, these aren't spice, these are the meat. Okay, not meat in case I was gonna say, let me collect myself for a moment. I cannot solve this equation, or I cannot solve this problem without some relationships. They are essential. First I said spice, but I guess you can eat without spice if you like bland food. And then I was going to say meat, but I didn't want to exclude any vegetarian. I really need to go vegetarian one of these years. I'm cutting back, but when will they meet? Goodness. Whole other can of worms. When will they meet? Right. Oh my gosh. I'm sorry. I'm a little scatterbrained right now. The equation, of course, is distance equals rate times time. Yeah? Distance equals rate times time. Okay. Specifically, however far train A goes is its rate times its time, because they have different rates, right? And however far train B goes is its rate times its time. Okay. When will they meet? Okay. Now I can start to piece things together. When I say they meet means they go the same distance. So that means the first train and the second train go the same distance. Right away, that lets me do a fun substitution. I can get rid of two variables right now. If these are the same, then these are the same. So I'm going to say rata equals rib. Make sense? If the distances are the same, then the other sides of the equation have to be the same as each other. So I took this thing, well, I took these two equations and glued them together. The transitive property of equality is a good way to explain it. If these and these are the same, these and these are the same, and then these and these are the same, these and these. It's easier to just understand it visually than for me to try to put it into words. You see what I'm saying, though, yes? Okay. So rate times time for the first train is equal to rate times time for the second train, because those are the distances and the distances are the same. That's probably the best way to phrase it. A professional would have practiced before he turned on the recording. But I've given this lecture so many times throughout the years. Okay. I know the rates. Excellent, I know the rates. That's something we can pencil in right away. I'll substitute those in as well. Fewer and fewer variables, that's what we're trying for. The first rate is 60, and the second rate is 65. Now, how about the times? Okay, there's one more piece of information in the problem, and I need to get rid of one more variable. So here we go. The second train leaves an hour later than the first train. So however many hours the first train is traveling, the second train is traveling 1 hour fewer. Yeah. So, like, for example, if you leave the station at 2 o'clock, then I'd be leaving the station at 3 o'clock. So if we meet at 8 o'clock, then you've gone 6 hours and I've gone 5 hours. However many hours train A travels, train B will travel 1 fewer hour because it was sitting at the station for that first hour. So put that into the language of algebra. And that's always the toughest part, is knowing how to put these into the language of algebra. Train B leaves an hour later, so however long train B travels, it's however long train A travels minus that hour it spends sitting in the station. There's no hard and fast rule. English is such a huge, complicated, like, English is so rich in what it can express that there's no formula I can give you for turning English into mathematics. If we were all speaking Esperanto, this would be a lot easier, but not English. There's probably hundreds of ways to express subtraction in the English language. We'll just have to think, what is this trying to tell me? What does this sentence mean, and can I express that? If I can express all the quantities in terms of numbers, then the relationships have to have something to do with numbers. So all I can say is I know it when I see it. Okay. I'm going to substitute this fellow in here. 60 TA equals 65 times, and parentheses again are crucial here, TA minus 1. This whole time is being multiplied by 65. So if it's being replaced with 2 terms, they have to be in parentheses so that the whole thing gets multiplied by 65. Okay, now we're just about ready to go. I'll distribute. I can subtract 65 TA from each side. So I'll subtract that expression. So on the right side, they cancel out. On the left side, well, it's like terms. We're combining like terms. 60 of them minus 65 of them leaves us with -5 of them. And on the other side, that's -65. Divide both sides by -5. That'll leave us with a positive answer. And now we want to put these back to the language of the problem. I could say something like, okay, that means train A travels for 13 hours. So when I say when will they meet, I could say they will meet 13 hours after train A leaves or 12 hours after train B leaves. Those are the same time. And then just to check, I could, I'll have to get a little creative checking here. I could check that the distance is the same for both. So 13 hours going 60 miles per hour has to be the same as 12 hours going 65 miles per hour. Now, both of those numbers are 780 miles. And so we're perfect. We're golden. We did it. That's the problem. So this one was dicey. We had 6 equations and 6 unknowns, and I kept introducing new information to lower the number of unknown quantities. So I reduced it from 6. Then we saw those were the same, so we broke it down to 4. Then I knew the rates, so I had 2. And then I could write 1 in terms of the other, and then I was down to 1. Once you're down to 1, you're ready to solve. But probably the trickiest thing in this problem is going from these 3 English sentences, having the spark of intuition to put distance equals rate times time, which anytime you've got motion, it's a safe bet that this will show up in a college algebra story problem. If you would like to study motion extensively, you can then take calculus, where we'll talk about, well, we'll get to that. No need to bring that into this lecture. But distance equals rate times time is a great one for college algebra story problems. If there's motion involved, probably we can treat it with this. All right. So hopefully, again, knowing how to solve any of these specific problems is not so important to me. What's important to me is that you can see how this set of 6 steps lets you flow through a story problem Because really the hardest thing about so many math problems is that they're daunting. You get a math problem like this and you say, where the hell do I even start? What do I do first, second, third? Have you noticed that if you have some kind of a difficult chore ahead of you, if you can just break it down into parts and say, all right, I can spend 5 minutes just starting this, it gets so much easier. Like if you can write the introduction to an essay, then it's so much easier to do the rest. These 6 steps are kind of an outline. It's a guideline, and it's an outline of where you should start and where you should plan on going as you're solving a math problem. Again, not hard and fast rules. You saw how I played with the order of these steps in these 4 problems we did, but definitely a good thing to keep in mind. So if you're working on the homework or you're solving a problem out in your life and you get absolutely stuck, let's try reading through these steps again. See if it jogs your memory. See if it helps you see where to start. Because so often, the first step is the hardest of the journey. All right, that is all for now. Join me in the next video. We'll be learning about complex numbers. Ooh, I love them. I love complex numbers. They are so much fun, and they're beautiful. They're beautiful. Complex numbers, oh my goodness. I will try not to go on too many tangents in the next video about how beautiful complex numbers are, but no promises.